Hello everyone, welcome to my presentation today. My name is Bludau, I'm a researcher at Fortiss, and today I'm going to present our paper called PR-SZZ, how pull requests can support the tracing of defects in software repositories. Information about defects or bugs in software repositories are an important asset to empirical software engineering research. The information is normally stored in issue tracking systems alongside the version control system, and these bugs form the foundation of many empirical studies. For example, they are used as training data for classification tasks such as defect prediction. SZZ is the standard algorithm used to extract these data sets about bug fixing and bug inducing commits from the version control system by first finding the fixing commit for a bug ticket and then tracing the bug introducing commit from there. Open issues in SZZ potentially reduce the credibility of studies relying on its correctness, and therefore we propose PR-SZZ, a new version of SZZ using additional development workflow data to increase the algorithm's performance. I will now first introduce the basics of the SZZ algorithm for those who are not familiar with the algorithm, and then explain our approach in detail, followed by an evaluation of our approach that also can be found in our paper. The original SZZ algorithm works in two steps, where it first maps bug tickets to bug fixing commits and then uses these fixing commits to trace bug inducing commits. For the first step, it uses an issue tracking system such as Jira or GitHub issues to get all bugs for a project. The bug identifiers are then mapped to references of said bug in the commit message. So in this example, we have a bug with issue identifier number 159. And the algorithm looks in all commit messages and searches for references to this bug. In this case, it finds a commit which states that it fixes number 159. This commit is then used as the bug fixing commit. And this process is done for all the bugs in the issue tracking system, and then we have a list of bug fixing commits. After that, the second part of the algorithm searches for the bug introducing commit by getting the changelog and blaming every changed line, meaning searching the last commit that modified the fixing lines. In this example, lines 21 and 25 have been changed in the bug fixing commit in order to fix the bug. So both lines are suspicious of being the ones where the bug was introduced. These lines have been changed in two different commits. These two commits form the list of potentially bug-inducing commits. However, when you look at the timeline, as line 25 was introduced in a commit after the bug was reported, the bug-introducing commit can be identified as the one that changed line 21. And so the algorithm finds all inducing commits. One fixing commit can have multiple inducing commits, and this can be a problem. I will talk about this a little later. Multiple additions were proposed since SZZ was first published in 2005. Most of these additions propose new filter or selection mechanisms to reduce the number of reported bug-inducing commits. And we will use these variants to later on evaluate our approach and measure our performance. Still, SZZ has multiple problems today. For the first step of the algorithm, fixing commits are often false positives because they are mismatching the issue identifiers in the commit message. This is because the first step of SZZ often relies on regular expression matching, which is quite error-prone in this approach. Also, many true positive fix commits cannot be found using the traditional approach. This can be seen in the image here. So for the issue number 1, we can clearly see that there is a commit that fixes this issue in the version control system. However, for the second issue, we don't have a reference in the commit message, and therefore we cannot trace this fixing commit. Our hypothesis here was that open source development better integrates the development activities and its artifacts, and therefore allows for a better or additional mapping to find more true positive fixing commits. In the second step of the algorithm, there are oftentimes too many inducing commits produced, which means there are many false positives due to the trace changes that were not directly fix related. If we look at commit number 7 and we expect here that this is a fixing commit, then all the files in the commit, so file A, B, C, and D, would be traced back in the history to find inducing commits. However, not all of the files are potentially related to the fix. So a filtering here would be appropriate to reduce the number of files that are traced and therefore reduce the number of false positive inducing commits. And also here our hypothesis was that open source development provides more fine-grained data to filter relevant changes and to reduce the number of false positives in this step. When I'm talking about open source development, I'm mainly talking about the workflows used to integrate changes from contributors to the main repository. And these workflows provide knowledge about how the features were developed. However, as seen on the right, different projects use different methods to integrate these changes, and the development history of how the change or how the fix was developed is not always persisted. Most open source repositories use a pull-based workflow, which means they use merge requests or pull requests to integrate their changes. And data about development activities is actually persisted in code management or code hosting systems, even after the pull requests are integrated and the branches are deleted. For example, in GitHub, if you look at a pull request, and a pull request can have multiple commits, and even if these commits are integrated using rebasing or squashing, the commits can still be seen in the pull request. So to recap, the traditional SZZ approaches only use issue tracking systems and the version control system to find fixing commits and trace inducing commits. We try to use additional meta information from code management systems such as GitHub, especially pull requests and feature development lifecycles, to allow for a more fine-grained analysis of defect data sets. Now that we have this additional data, I want to show you how it can contribute to the extraction of defects dataset. In the first step of the algorithm, we want to find fixing commits. And I've already shown you the figure on the left side where we are not able to trace back the fixing commit for issue number 2. But in this case, if we look at the right, if we use pull requests, we can have a better integration between issues and the actual solving of the issue using the pull request. And we can use the resolving commit of the pull request to find the fixing commit for the issue. This is not only true for integrated issue tracking systems such as GitHub issues and GitHub pull requests, but also for third-party issue tracking systems such as Jira, because also Jira issue identifiers are mostly mentioned in the related pull requests, and I will talk about this when we talk about the evaluation of our approach. For the second step of the algorithm, meaning tracing bug-inducing commits, we can also use pull requests to reduce the number of traced files. So let's assume in this image, and please concentrate on the yellow marked areas, we have commit number 7, which is a fixing commit. So this commit was marked as fixing from the first step of the algorithm. We now can see that all files, file A, B, C, and D, would be traced using traditional approaches. However, when we look at the pull request, we can filter the inner commits of the pull request and see that only file A and B are fix related. So we would only trace file A and B with our new approach. Looking at the traced commits for file A and B, we find that commit number 1 and commit number 3 are potentially inducing bugs. However, now we can look at the suspicious pull request for commit number 3, and we find that only the second inner commit is really inducing a bug, and we can ignore file C from the inducing commit here. So now let me jump to the evaluation of our approach in our paper. For that, we collected 6 open source projects with different workflows and from different backgrounds that can be seen on the table on the right. We collected data from multiple issue tracking systems, for example, Jira and GitHub issues, and also pull requests can be labeled as bugs. And therefore, we collected more than 40,000 commits, more than 30,000 pull requests, and more than 15,000 distinct bug reports. We have seen that an adoption of pull-based workflows can be seen for every of the project over time, and every major project here uses a pull-based workflow. We then performed a quantitative and a qualitative evaluation for both steps of the SZZ algorithm and compared them with the performance of existing variants. And for the evaluation, we labeled 100 elements of every project manually to be sure that the quality of our approach is not dependent on the quality of existing approaches. For the first step of the algorithm, meaning mapping bug tickets to bug fixing commits, we see that comparing our approach to existing baseline approaches, 18% of bug tickets can be additionally mapped to a fixing commit using our approach. And this is independent of the issue tracking system used, as can be seen on the table on the right. However, the number of mapped bug fixing commits is still quite low for some issues. And this is because not all issues are closed and fixed, because sometimes an issue is reported without a real problem, because the problem is irrelevant, because it is a third-party problem, or there was a misunderstanding by the reporter. So we have also executed a manual evaluation, and we can see that the precision, recall, and F-score are higher for our approach. So the high recall on all projects shows that additionally fixing commits can be correctly mapped, and we can find more and correct fixing commits than all baseline approaches. For the second step of the algorithm, meaning tracing bug-inducing commits from the fixing commits, we can find that roughly the same number of inducing commits can be found for the fixing commits using PR-SZZ or baseline approaches. This is because both approaches use git blame to find inducing commits. You can see the baseline approaches in the table on the right, which are also the same approaches we showed earlier in the slides when we talked about related work. Our approaches are marked with the yellow boxes. When we look at the manual evaluation, we can see that PR-SZZ has a higher performance for finding bug-inducing commits. When we apply a selection mechanism, this leads to the highest precision on all investigated projects using PR-SZZ compared to baseline approaches. Also, the recall when using PR-SZZ without selection mechanism can be higher than using baseline approaches. We have discussed quite extensively that the performance of existing SZZ variants is highly depending on the project characteristics. For example, if we have a workflow that doesn't use rebase or doesn't use squashing of commits when integrating changes, we see that PR-SZZ, the effect size of PR-SZZ is mitigated. To conclude, we see that pull requests can support the search of bug fixing and inducing commits. PR-SZZ is able to find additional bug fixing commits, and we report an increase in precision and recall, elevating the F-score on average by 40 percentage points. For the second step of the algorithm, we see that we gain 16 percentage points in precision using PR-SZZ. However, these performance gains vary depending on the project characteristic and the used development workflow, and we have discussed this in our paper. Thank you very much for your attention.